Hello everyone. Welcome back to The Joy of Coding at Portland State University. Let's continue our discussion and exploration of Java's collection API. If you haven't done so already, I recommend that you review part 1 of this screencast, in which we learned about Java's class hierarchy for collection classes that hold and organize objects in various structures like lists, maps, and sets. In this screencast, we'll dive into the abstractions that allow collections to be sorted, look at Java's type-safe enumeration language feature, and learn about a JVM system properties. There's a lot of good stuff here, so let's get started. So we've learned about lists and sets, which group objects together. And with sets in particular, they use the equals method to determine whether or not an object already exists in that set because objects in the set are by definition unique. Now let's talk about how the collection APIs compare objects. Because if you get something like a sorted set, you want to retain a particular order in which the objects appear within that collection. So there's an interface in Java called JavaLang Comparable, which is said to provide a natural ordering over objects. These are objects that inherently know how to order themselves. So things like strings, right, alphabetical order, or integers, doubles, all the numbers, etc. They implement this comparable interface because an instance of this class knows how to order itself with regards to another instance. And the way this is achieved is by implementing the compare_to method that's inherited from comparable. The semantics of the compare_to method are as follows. So you're comparing two objects, x and y. X is the receiver, is the method on which compare_to is being invoked. And compare_to takes another object, y, which is the thing to compare to. The compare_to method will return a negative number if x is less than y. If the two objects are equal, then 0 should be returned. And note here that if the compare_to method considers two objects to be equal, then you should have the same semantics in your equals method. So compare_to and equals must return the same value. If the x object is logically greater than the y object, then a positive int should be returned. The comparable interface has a generic type that specifies the type of object that it can compare itself to. Almost always, an object knows how to compare itself only to another instance of that same class. I suppose it's conceivable that you could have an integer that knows how to compare itself to a string, but that doesn't make too much sense. Almost always you're comparing to another instance of yourself. So classes and methods that sort objects, so things like sorted set, will use the comparable interface when sorting objects, unless you instruct it to do otherwise. So here is an example of using natural ordering, of using that comparable interface. We're going to see how we have a class that represents a box of cereal, and cereals are naturally sorted alphabetically by their name. We declare our cereal class, and because it has a natural ordering, it implements the comparable interface. Every cereal has a name and a price, and it's got some constructors that set those fields, things like that. What's really interesting in this class is the compare_to method. A cereal compares itself to another cereal, C2, by, comparing its name. And so really what we're doing is we're delegating the responsibility for comparing two cereals to their names. So the compare_to method simply returns how this cereal's name compares to the other cereal's name. Now, because I overrode compare_to, I also need to override equals to make sure that two cereals with the same name are considered equal. So how do I do that? Well, I implement the equals method to first check to see whether or not I'm being compared to an instance of cereal. If I am, then I say, hey, is my name equal to the other cereal's name? If none of these conditions is true, I return false. Because I overrode equals, I should really override hash code so that two objects that are equal have the same hash code. And how do I do that? Again, I delegate to the name. This delegating to the fields is a very common strategy for implementing equals in hash code. In this case, the hash code of the cereal is the same as the hash code of the string. This will certainly work and is good enough for this example. Again, because cereal implements the comparable interface and provides a compare_to, it is said to be naturally sorted. So this means that you can use a serial object in any collection that sorts its contents. Here in the main method, we do some stuff with our serials. We're going to create a sorted set of serial, which is a tree set, and we're going to add some serial objects to it. We're going to add a box of Total, some Raisin Bran, some Sugar Crisps. They all have different prices. And then we're going to print out that sorted set that we created. And now when we run the example, we see that Raisin Bran, Sugar Crisps, and Total are all printed out. And notice that they're printed out in alphabetical order because when the cereals are added to that tree set, the compare to method of the serial class is used to determine what order they are stored in and therefore what order they're iterated over. So the nice thing about natural ordering is it allows the author of the class to specify how instances are compared to each other. So natural ordering is really great, but there are also times where you want to have a custom ordering or impose your own ordering on objects. In this case, you would use an interface called comparator, so not comparable, comparator, that takes two objects and sorts them by some criteria, most likely other than their natural ordering. A comparator is said to specify a total ordering over a set of objects. Comparator has a compare method which takes two objects and returns an int with that same negative, zero, positive semantics as the compare to method of comparable. Now, unlike comparable, whose compare to method must have the same meaning as the equals method, a comparator may or may not choose to respect that equals method. Let's say that you're looking to sort strings on their length instead of alphabetically. There, it wouldn't make sense for two strings with the same length to be considered equal. Just like comparable, comparator has a generic type that specifies the type of object that is being compared. And so a comparator can be used to create a tree set or a tree map, basically these sorted collections. They're provided in the constructor, and then that comparator is consulted as objects are added to the sorted collection. Here's an example of a comparator. It compares boxes of cereal based on their price. So now we're going to sort them based on their price. Here I have a class called serial comparator. This is completely separate from the serial class itself, right? It implements the comparator interface that compares two cereals. So therefore, it'll have a compare method that takes two serial objects, O1 and O2. Its implementation is pretty straightforward. It goes and it gets the price of each one of those boxes of cereal and says, hey, if the price of 1 is greater than the price of 2, return 1. If the price of cereal box 1 is less than the price of cereal box 2, then return -1. Otherwise, return 0. So that's the logic of the compare method. Here's where we'll see comparator in action. We'll create a new tree set object, a tree set of cereal, and provide it with a new instance of the serial comparator class. And now, as instances of cereal are added to this sorted set, they will be sorted based on their price. And you see that when we print it out, right? We added Captain Crunch, Trix, Count Chocolate, and Fruit Loops, and then we print them out ordered by their price. The least expensive one is first. So Fruit Loops at $2.45, followed by Captain Crunch, followed by Trix. Again, these aren't in alphabetical order, they're ordered by their price. Now you may have noticed that we added 4 boxes of cereal and only got 3 out. Now why do you think that is? Well, it's because 2 of them had the same price. And our comparator treats 2 boxes of cereal as equals as the same if they have the same price. This probably isn't what you want, right? So in this case, what we should probably do is go back and augment our serial comparator to break the tie. So, I don't know, something seems logical, like if 2 boxes of cereal have the same price, then we should sort them based on their name, for instance. And that would provide a more inclusive total ordering of our boxes of cereal. Another important class in the Collections API is a thing called Java Util Collections. This is collections with an S on the end, it's plural. And this has a bunch of static methods that are helpful for working with collections. And notice that if you go and look at the API documentation for this, you cannot instantiate this collections class. It's got a private constructor because all it has is a bunch of functions on it, right? It's like the math class. It's not a class that is meant to be instantiated. It's a class that holds a bunch of functions. So you can get things like the maximum element in a collection. And so you can pass it any collection, and it'll use the natural ordering of those objects to find the maximum value. The nCopies method will return a new list object that contains a given number of copies of a particular object. There's a method called singleton where you give it an object and it returns a set that contains one and only one object. And this is good when you've got a set and you just want to send one object to it. And it's also got a sort method that will take a list of objects and it will sort them using a particular comparator. Because lists are not sorted. And so if you want to convert between a list and a sorted set, you would use a method like the sort method here. Another interesting method is unmodifiable map, and they're unmodifiable collections, unmodifiable lists also. But the whole idea here is that you provide this method a map object. And remember, maps can be changed by anybody, right? Put is a public method, and so then any code can invoke put and can change the collection. You don't always want to do this. Sometimes the contents of a collection are something that ought to be managed similarly to the way a private field is managed, right? You want to make sure that you're providing good data into it. And so then if you, what unmodifiable map lets you do is create, it's not exactly a copy, it's really, you get a map that wraps the other map that allows you to get information about it. You can call entry set, you can get the value for a particular key, but if you attempt to modify the map, like call put on it, it'll throw a runtime exception, an unsupported operation exception. And this then protects your map from being modified by code that either inadvertently or maliciously is modifying your map. Java util arrays is like collections in that it's got a bunch of static methods that help you work with arrays. So it lets you convert an array of objects into a list. And if you go to modify the list, it'll modify the underlying array. This is also where there are methods like doing a binary search on a bunch of ints for a particular value. If you want to compare two arrays to see if they're equal, meaning they have the same contents in the same order, you can do that here. Also allows you to populate an array with particular values and then do an in-place sort of arrays. And while the examples I have here on the slides are all int, these methods are overloaded to take any type of primitive object and just objects themselves, object arrays themselves. The Java programming language provides something called an enum, which is a lot like a class, but it has a predefined set of instances. If you're familiar with C and C++, they have an enum type also. And the whole idea is that when you want to model something that only has a certain set of values, let's say that you want to represent a color that's used to draw something, and you've got a very limited palette, and so you've only got 12 colors that you can choose from. Really what you want is a color class and for it to only ever have 12 instances. That's all you want. You can't create a new color. We only support a handful. And so Java's type-safe enumeration is a lot like a class in that it's a type in the language, and you can import it. You can have variables and parameters of those types. But unlike constants, which are just public static fields of any type, you can use an int, you can use a string, or whatever. The fact that these are type-safe enumerations provides a lot more safety for the code. You can change information about it without having to recompile everything else, so nothing is inlined. And type-safe enumerations, unlike just plain old constants, have toString and equals and hash code methods that are generated by the compiler to have useful information, useful values in them, so that you don't have to write yourself. They also implement comparable, and so then you can add them to sorted sets and collections. It's all good stuff. It's a lot of syntactic sugar and just the right amount of code generation to give you something useful. So here is an example of using a type-safe enumeration. We'll have days of the week. Okay, in our calendar, there are 7 days of the week. Sunday through Saturday. And the way that you create one of these enums is the following. Here, you declare an enum type usually within another class, although I suppose you could do it as a top-level class. Here we declare it inside another class called enumerated types. And I say private enum day. So private means the enum can only be referenced inside this class. I enumerate the instances of this class: Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, right? Those are the 7 and only 7 instances of the day type. And for the sake of example, we have a method that will translate a day into its Spanish name. And you can do this with a switch statement. So enums can be used as the target of a switch statement in Java. And so here we go, right? We switch on the day, and then for each value, there is a case statement that will return the Spanish equivalent of that day. You'll note that the switch statement has a default branch that if there is a value of day that this code does not know about, it will throw an illegal argument exception. If you add a new day enum and don't modify the en español method, you'll get a runtime exception, which seems reasonable. This main method here shows how you can work and reference enum types. So what I do is I'm going to create a sorted set of days of those enum instances. I'm going to then add Wednesday, Monday, Friday, and we're going to print those out. And as we see down below, when I print out the enums that have been added to the sorted set, because enums implement the comparable interface, they know how to compare themselves, they are printed out in the order in which they are declared inside the code. And that's because every enum type has a notion of its ordinal, the order in which it appears inside its declaration. Additionally, I can iterate over each element of that set and print out its value in Spanish, and there we go. So the way we reference these is that we just say day.Wednesday. It's a lot like a static field, right? It looks a lot like a constant, but what we get is an actual object which is strongly typed, has a limited number of instances, and then has things like a toString method that'll print out all caps Monday. It'll have the ability to sort itself because it's comparable, has equals and hash code implemented, all sorts of good stuff. And the syntax to declare these is much simpler than creating your own class and having to override all those methods. Now, if we look at how type-safe enumerations are implemented, it's kind of interesting what's happening there at the bytecode level. Basically, what's happening is we're creating a little Java class that extends the class Java-lang enum. And enum is a thing that provides the equals hash code and ordinal methods. All that stuff is final. The toString method is what ultimately is implemented by the subclass of enum. The compiler also adds static methods. There are a couple of static methods that are added to the enum class. Hey, let's say you've got an enum that represents coins, U.S. coins, pennies, nickels, dimes, etc. If you want to get all of the enum instances, you would say coin.values, and that returns an array that has each instance of the enumeration, so you can iterate over them that way. Or if you want to get an enumerated instance of a given name, you can use the value of method. You give it the name as a string, and so say, I want the coin for dime, and you can do it that way. Of course, you could also just say coin.dime in all caps. But this is, this way, if you want to something dynamically and just pass in any old string, it'll do that. And if it doesn't exist, it either returns null or throws an exception. I can't remember off the top of my head. Now, it's possible that you can add more behavior to an enumerated type. And this can be really quite powerful at times. So let's say that we want to have an enumerated type that represents an arithmetic operation. So we'll have an operation for plus, for minus, for multiplication, divide, etc., etc. And these are binary operations, and so they take two arguments, sort of a left and a right to the operation. And not only do we want to just say that there's an operation out there, but we want each operation to be able to have some behavior that's unique to it, to actually perform the operation. So our enum not only is just the declaration of an enum object, like all caps plus, but we also can provide implementations of behavior. So for instance, an eval method, which will evaluate two operands in the context of the particular operation. So the eval method for plus is x plus y. And then also we want to be able to get the symbol, the character that represents the plus operation, which will be the plus character. So similarly for minus. So we could add some more operation declarations here. But also in the enum type, maybe I could have put this first to make it a little bit more understandable, is that we say that the operation has a couple of methods, and we just declare the signature of the method. It's a little bit like an interface, right? We say, hey, it's an abstract method. Every operation has a method called eval, which takes two doubles and returns another double, and then also get symbol, which will return the car for that operation. Here's an example of how to do that. We go get all of our operations, so plus, minus, times, and divide, all of them. We iterate over them, and then we will perform each operation with two operands, 5 and a 2. And then we'll print out, so 5, and then whatever the operation symbol is, and then concatenate 2, and that equals the result of evaluating that operation with 5 and 2. So when you run this program, you'll get 5 plus 2 equals 7, 5 minus 2 equals 3, multiplication, divide, etc., etc. And so this is nice. A lot of the times you have classes that only have a couple of instances. And with enums, you can either have sort of something super easy out of the box, like you had with the day enum, or you can have something a little more complex that has custom behavior for each enumerated instance, something like operation here. And finally, I want to talk about Java util properties. Now, properties is a lot like a map in that it maps one string value to another string value. But properties are meant to be used to store configuration information, either about the Java virtual machine itself or an application. And these can be written to files, and so you just have these nice, key value pairs with an equal sign between them to configure things. So a properties object has the ability to get and set a particular properties value. You can also list all of the pairs in a properties. You can send that to a print stream. So this makes it easy to print a properties to system.out. And you can also load and store properties from some source, like a file or a database or someplace else. So properties has been around for a long time. It implements the map interface, but it's not a map of strings, actually a map of objects for backwards compatibility reasons. But that does allow you to do things like have an int as the value of a property. There's an interesting instance of properties that's called the system properties. And these are configuration options or just demographic information about a Java virtual machine that are all available via this particular instance of properties. System properties, many of them are set by the JVM itself, sort of internally as it starts up, but you can also specify your own system properties by using the -d option to the Java command when you run the Java virtual machine. We'll see an example of that shortly. Inside the code, though, you can get at the JVM system properties by invoking the static getProperties method of Java System. And you can also just get the value of a particular system property by just saying getProperty from Java System. System properties are also referenced by the wrapper classes. So there is a method called I_integer.getInteger, which will get the integer value of a system property of the given name. Basically what this does is it goes and looks up the value of that property within the system properties object and then attempts to convert it to an integer. So here is an example of using system properties. Basically what it does is it goes and gets the system properties, prints them out, and then looks to see whether or not a particular system property value has been set. In this case, it's edu.pdx.cs4nj.debug. This is a Boolean value, and it'll determine whether or not it's true or false. So the first thing we do in our main method is we go and get the properties object, and then we print out all of the properties to system.out by invoking the list method. And we'll see on the next slide what that actually looks like. Then we want to see if a particular system property is set. Again, this edu.pdx.cs410j.debug. We go and determine that by invoking the getBoolean method of the capital B Boolean class with that particular name, and that'll return a Boolean value, true or false, whether or not that system property was set. And we'll say, hey, are we debugging? And then yes or no. Let's take a look at how we run this class. We've already compiled it into ~classes, but when we invoke the Java virtual machine, we say Java and then -D edu.pdx.cs410j.debugs equals true. This sets the system property, right? That -D sets a system property. And then we run our main method. So we see that it lists all of the system properties. And look at all the stuff that's there. You can get information about what version of Java you're running, who the name of the user is, who provided your JVM, what operating system you're running on, things like the home directory for the user or the directory in which it's currently being run. All sorts of great stuff. But if you look towards the bottom, the ones right above the file separator, you'll see that edu.pdx.cs410j.debug is set to true. So that's the thing that we put on the command line, and now it's represented in this list of system properties. So if we go down to the very bottom of the slide, that's where we print out, hey, are we debugging? The answer is yes. So using system properties is a way to enable debugging or other diagnostic or other logging information for your Java programs. And you'll see that a lot as you work with third-party software. That brings us to the end. So the Collections API is what we've been talking about in this screencast and the previous one. What the Collections API does is it provides really fundamental capabilities to every piece of Java software. Every program works with objects and usually needs to gather objects together, and that's what collections are so good at doing. Now, different collections classes have different capabilities and different characteristics that the programmer can use to good effect. So some collections will sort themselves, some of them have indexes into the collections, some of them store unique objects. Collections API, I think, is a great example of object-oriented programming. You have a rich hierarchy of both interfaces and classes that allow it to not only be understandable but also extensible and make it so that you can leverage these same abstractions in your code. And because the collections are so popular, there are a number of language features that really augment them. Everything from the enhanced for loop for iterating over the contents of a collection to generics that allow you to have strongly typed collections so you know exactly what type of data you're working with. And wow, that's it. We've covered a lot of material in these last two screencasts, and I really appreciate you sticking with it. I hope you've enjoyed what you saw and are curious about how you can apply these concepts and tools from the Java Collections API in your projects for the joy of coding here at Portland State University.